This computer. Okay, so today we're going to we're going to review the expressions for the 1D and 2D Fourier transforms. We are going to look at the units typically used, and we're going to spend a lot of time looking at the spatial patterns associated with various parts of K-space. So that'll be useful for some of the upcoming homeworks. We'll look at how modifying the Fourier transform affects the images. And we'll also look at how to compute basic Fourier transforms and look at basic Fourier transform properties. Okay, so if you were at the supplementary session 1, you know that in that session, we looked at representing signals and images, either in 1D or 2D. And there we were using delta functions to represent our signals. And so essentially, we said any signal could be represented as a sum of delta functions appropriately weighted and shifted. The Fourier transform takes a different view of signals. And so, for example, this signal here is going up and down, up and down. And if you were to represent this with delta functions, then you'd have to have a lot of these delta functions of different heights and shifts to represent that signal. Okay, and so you might imagine maybe you need 20 delta functions to represent that signal well. But it turns out that that signal is just made up of these Fourier transforms here. So it's taking this sinusoid of this frequency with some amplitude, adding this one of a different frequency, and then adding this one of a different frequency. And those three together give you this signal here. And then if we look at the amplitudes of each of those signals, and so here would be the amplitude of the first signal, the second component, and the third component, these amplitudes are essentially the amplitudes of the Fourier transform. So the Fourier transform is just telling you how much of each frequency you need to create the signal of interest. So the 1D Fourier transforms is fairly straightforward. You take your signal, g of t, and then you multiply it by a complex exponential, e to the minus j 2 pi ft, where j is just the square root of -1. And so that's a complex exponential. So that is the Fourier transform, And we typically use if g is our function, we typically use big G to denote the Fourier transform of that function. The inverse Fourier transform is written as follows. Given the Fourier transform, we multiply it by complex exponential, which looks exactly like what we used for the Fourier transform, except there's no minus sign here in front of the j. And then our function g of t, we recover from the Fourier transform g of f. Okay, and we can denote that as either the forward Fourier transform f or the inverse Fourier transform f to the -1. So let's talk a little bit about the units. Especially for MRI, we'll use both time sometimes when we're talking about waveforms. And so in this case, we'll use time is in seconds, and then then f is in cycles per second, or also called hertz, Hz. But since we'll also talk about things as a function of space, we also want to denote space, and typically the units will be either centimeters or sometimes millimeters for imaging. And then we use k sub x to denote the spatial frequency. And if x is in centimeters, then the spatial frequency is in cycles per centimeter. Okay. Very important thing that was Dr. McVeigh pointed out in lecture, that Euler's formula is very important for understanding Fourier transforms, and also we'll see it plays a key role in MRI. So it's good to get comfortable with the Fourier transform. The main thing you need to know is that basically anytime you see e to the j theta, you can think of it as cosine theta plus j sine theta. And so typically we represent it on the unit circle. And so e to the j theta is just a phasor, okay? And as theta changes, it just maps out along the unit circle. So if theta is positive, you go this way. If theta is negative, you would go this way, all right? And so the components of e to the j theta are simply cosine theta and sine theta. So with that, we can expand the word, we can take that complex exponential and expand it out into an integral that involves cosine, an interval that involves sine. And so essentially we're taking our function and we're comparing it or multiplying it with the cosine function, and then we're integrating it. And so this is a form of what's called an inner product, which you may have heard of either in physics or linear algebra. And so it's essentially asking, how much does g of x look like cosine 2 pi kxx? Okay. The more g of x looks like that cosine of that frequency, the larger this integral will be. And similarly, because there can be phase shifts, we will also have to ask, how much does g of x look like sine of 2 pi kxx? And so multiplying g of x by the sine of a certain frequency and then integrating it tells us how much of g of x is sort of looks like sine of 2 pi kxx. So one thing to notice is that if I have sine 2 pi kxx, then the wavelength is just 1 over kx. All right. So the 2D Fourier transform is what we primarily use in this course, especially for the MRI section. And so its definition is also fairly straightforward. Now we have a two-dimensional function g of xy, and now our complex exponential just has a kxx term and a kyy term, and then we integrate over dx and dy. On the inverse Fourier transform, we take the Fourier transform, and now we multiply by this complex exponential, and it's the same as we used before, except there's no minus sign. Okay. So notice in the textbook, for some reason, Princeton use U and V for KX and KY. We will use KX and KY because that's sort of the standard in the field for medical imaging. And so it's good to get familiar with that notation. Okay, so we're going to spend some more time now talking about how do you interpret the 2D Fourier transform, because that's something that not everyone has seen before. So we can write out the complex exponential in terms of a cosine term here and a sine term here. And so let's see what happens with different combinations of kx and ky. So in this case, kx here is greater than 0, and we're assuming ky is equal to 0. Okay. So ky equals 0 means there's no variation in the y direction. There's the frequency in the y direction is 0. So that means no variation in the y direction. And all we have is a function cosine 2 pi kxx. So this only varies as we move along in the x direction with a wavelength 1 over kx. Okay. Similarly, in this case, kx equals 0, right? So this whole term here, we only have this term here, we only have the kyy part of it. So we have cosine 2 pi kyy, and therefore there's no variation in the x direction. There's only variation in the y direction. And then finally, we could have both 2 pi kxx and 2 pi kyy. And now we see that this function varies both in the x direction and in the y direction. And now the wavelength is given by 1 over square root of kx squared plus ky squared. You can derive that here with some trigonometry, which we're not going to go through, but essentially, if I have 1 over kx wavelength in this direction and 1 over ky wavelength in this direction, then this wavelength here is given by this expression here. Okay. And then this theta, the angle at which this plane wave is going off at, is given by arctangent kx, ky, right? So this is in terms of x and y. And one thing that's sort of useful to remember is if I give you a point in the kx, ky plane, okay, let's say I say there's some point in my Fourier domain, then what you can do is you can say, well, I just draw a vector out to that point, okay? The length of that vector by Pythagorean theorem is just kx squared plus ky squared, okay? So 1 over that is just my wavelength. And then this angle here, theta, tells me the angle at which that wave propagates. All right, so that's useful to remember. So this is a useful picture to remember. So we'll look at some examples of that as we move along. So once again, here are from the book, figure 2.5, some examples. And remember, we're going to use, this is going to be kx, ky. And let's just look through this. So this is saying kx equals 1, ky equals 0. So that makes sense. There's only variation in the x direction. There's no variation in the y direction, right? So this only depends on x. And here, the frequency kx equals 1, so the wavelength would be 1. So this means this repeats with an interval of 1, so it's going from here to here, I guess. Now, kx equals 2, and so now the period has, the frequency is doubled, so the period is halved, okay? And here, kx equals 4, and so now you can sort of see we're at a much higher frequency, and the wavelength has gone down even more, all right? Now here we look at what happens when we keep, you notice here we're keeping this variation, the kx, the same. So these are all kx's. And so all of these, the ones on the bottom here, if you look at it moving along the x direction here, the spacing, they all have the same spacing, right? They have the spacing that this one had, okay? The same wavelength. But notice we're varying the ky. So in this case, it's 1, 2, and 4. And so here, if I go from here to here, that's 1. If I go from here to here, that's 1/2. If I go here to here, that's 1/4. And so essentially you can sort of see as I keep the kx the same, but I increase the ky, that wave pattern starts to tilt because it starts off with mostly variation in the x direction, and then as I add variation in the y direction, it starts to become more diagonal. Okay. So we'll look at some examples of that and give you guys some problems to work on. Okay, so probably the most important thing today is to get a feeling for what is k-space. That's what we call the Fourier domain. Okay. And essentially, it's basically, if we consider our image here, that's as a function of x and y, and we take the 2D Fourier transform of it, and then we end up in a space kx, ky. In this case, I'm just showing you a 2D Fourier transform. If we had a 3D object, we could do a 3D Fourier transform, but to keep things simple, we'll make it 2D. And so this is what we want to get familiar with. This is k-space, okay? So let's talk about how to interpret k-space. If I give you an example like this, you want to be able to tell me sort of what are the features of this k-space, right? The first thing we're going to look at is what does the center of k-space represent? Okay, so we'll jump right away to the 2D object. And so in this case, I just put in at the center of k-space, kx equals 0 and ky equals 0, right? And so this term goes away. And so I just integrate gx over y over dx dy. And so that's essentially just the mean value of my image, okay? And that will tend to be, for most sort of biological objects, that will tend to be the largest value, of one of the largest values in k-space. And so if we go back here, you can sort of see here, the brightness indicates how big are the Fourier transform coefficients. And you can sort of see it's biggest sort of in the center, that corresponds to the center of k-space, and the signal dies off as we go out to farther parts of k-space. All right, so the center of k-space represents the mean value of this image, okay? And then everything else, you can think of an image as sort of a mean value plus then lots of details added on top of that. The mean value typically has the most sort of, typically is associated with the largest coefficient, which would be at the center of k-space. Okay, so let's take a look at some k-space examples. So this is kx, this is ky, and this once again, this is the center of k-space here, okay? So that's the part we just talked about. And now we're gonna look at, see what happens as if we go off along kx or ky, or even along both angles, and sort of see what sort of patterns those correspond to, okay? So let's say I pick a point here, shown by the green, And that is, I've gone off on kx, ky equals 0. So this corresponds to a pattern that varies only along the x direction and with some wavelength, where this would be, 1 over kx. Okay. Now let's say I go out farther into k space here. So it still only has variation in x, but now the wavelength is smaller because I've gone out to a higher frequency. And so this corresponds to a higher spatial frequency here. If I move along the other axis and I go here, now I'm along this axis where kx equals 0. So I end up with this corresponds to an image that only has variation along the y direction with some wavelength. And if I go further out, I still only have variation along the y direction, and now the wavelength is just smaller because I've gone out to a higher frequency. Okay. And finally, if I go out both along kx and ky, then I have variation in both x and y direction with some wavelength. Remember this one here is 1 over square root of kx squared plus ky squared. Okay, so these are some examples. What you're seeing here on the top row is the Fourier components that we're going to add. This is sort of like the cumulative sum of those components. So start off with the sum and the cumulative sum are the same. I add this component here, and now the Fourier transform is here, and I add this one. And so as I add each of these components, this is showing me the image that I'm getting by adding these components. As you sort of see, as I start adding these different components, my image starts shaping up into something that looks like possibly a head. Whoops. And then as I add more and more components, you sort of see the details filling in. And over time, I end up finally with something that looks like a head. Okay. So basically saying that every image is sort of a sum of all these Fourier components. Okay. So we're going to play a movie here. And what you're going to see here on the left is the Fourier transform. And here is the image that corresponds to it. And so at the beginning, all we have is a center of case space. So we just have sort of the overall mean value of my image here, okay? And as I play the movie, oops, the media is not found. Okay, sorry about that. Huh, that's weird. Anyways, I'll put that in. I'll put that picture on on Canvas. But essentially, what you should sort of see as we acquire more and more of K space, this image will look better and better. Okay, so we'll put the movie on Canvas. All right, so let's talk through some examples here. This is a example where we have over here, we have our object, our image, and this is its Fourier transform. And once again, the center of case space is just the mean value of that image. And now what I've done here is I've arbitrarily in MATLAB just zeroed out all these values here, okay? And so remember, the values over here, for example, the values out here would correspond to edges that are changing as a function of x. And so what we expect to see is that the edges that we see as we move left to right are going to be more blurry. And in fact, if you look here, this edge here, oops, is pretty sharp. And you sort of see this nice detail in these edges here, okay, as we move along here. And then here in this image, you notice that that edge now is quite blurry. And also we're losing all that detail here. Whereas the edges going up, down, that edge is still fairly sharp, okay? We can play the same game here where now I've zeroed out the coefficients here. So remember, this corresponds to edges in this direction, okay? And so this would correspond to getting rid of edges like that. And in fact, if I zoom in on this image here, that edge that used to be very sharp is now fairly blurry, okay? So I've lost that information about sharp edges as I move up and down. And in this case here, I've gotten rid of all the information sort of edges, both up, down and left to right. And so here, if we look at our image and we zoom in on it, we see we've lost a lot of the detail, okay? So the key is the outer parts of K space, whoops, these all carry the detail, okay? So basically, I've only kept this part of the Fourier transform. So you can sort of still tell it's a brain. It's just a very low resolution picture of the brain. And it's because it's low resolution, it's missing all the Fourier components out here in Fourier space that carry the very fine information about fine detail in the image. We can play a similar game where this is my image and this is Fourier transform. Now we zero out the center part of K-space and we only keep the information here, okay? Remember, these coefficients correspond to edges that look like this. And if you notice that we zoom in, that's really what we've kept in this image is mostly we've kept all these sort of vertical looking edges, okay? And we've lost the horizontal edges, okay? Okay, so then we can play a similar game where we keep these edges here, the information here, that corresponds to edges like this, and we've lost the information at edges out here. And then we zoom here in on this image, you notice that these edges are kept pretty well, but we've lost these other edges here, okay? And similarly, we can just zero out the center of K-space. This was the part we kept before to have our low resolution image. Now we've zeroed this out. All we've kept is the information about the edges, all right? And therefore, if you look at the image, this is essentially the high frequency component of my image. It's just all the edges in my image, okay? So this is a form of edge detection where you're just only keeping the high frequency information. Okay, the other thing that happens, sometimes we get artifacts in MRI and other modalities. And so here, what I'm showing you here is sort of on a different scale. This is where the Fourier transform of the image is. And now I've added this spike, and you'll do this in one of your homeworks coming up. And so let's see if this spike makes sense. Remember, I said if this, I'm in this KX, KY plane, right? And if I draw a vector out to that spike, then the perpendicular to that vector tells me what the edges should look like. And in fact, that's what the artifact has. It has edges that are going like that. Similarly, in this case, if I draw a vector out to here, it should have edges like that are perpendicular to that vector. And that's in fact exactly what we see in our image. So we're seeing the image, and then that spike is putting a lot of energy in at a certain frequency. And so that's superimposed onto my image. Okay, so now what we're going to do is we're going to use the chat feature. And what I'd like you to do is, this is a sort of mix and match. And so first of all, A just goes with this. So that's nothing. So you're going to sort of compare and try to match B, whoops, B, C, or D with 1, 2, and 3. And so in the chat, just put in, for example, your answer. So it could be some example answer would be like, B1, C2, D3. That's not probably the answer, but that's just enter in your answer. So we're going to give you about a minute or two to look at that. And just put in your best guess, just so I can get some feedback as to sort of what people are thinking. So take a look at these images. The slides are available also on Canvas if you want to zoom in on them. And we'll take a little break here and we'll resume once you've sort of entered in some answers. Okay, so far there's only one response, so I'll wait another minute. There's 7 guests, so once we have at least 4, we'll proceed. So just please, in the next minute, just enter your best guess, and then we can proceed. Thanks. Okay, there's some answers. It looks like some people may not be online, so let's see. For those of you who did, thank you for submitting an answer. So thanks, and we'll proceed. So there's some diversity in the answer, so I think that's good. So let's talk about that. Yeah, so let's take a look at the most of out of these 1, 2, and 3. So 1, 2, and 3. Oops, here we go. So 1, 2, and 3 are the Fourier transforms. Which one of these has the most information? Is it 1, 2, or 3? You can put in chat, or you can just pipe up and say. So is it 1, 2, or 3 that has the most information? Okay, so there's an answer 3. Okay, so let's look at that. So this has got information here. Okay, and there's the answer for 1. So in fact, actually 1 has the most information because here I've only zeroed out the center of K space, and there's information here all around here. These both have lost a lot of this information this way and this way and this way and this way. Okay, so you can think of the area that's blacked out is much greater in 2 and 3 than it is in 1. So in some sense, we would expect the Fourier transform of this one to have information about edges both up, down, and left to right. And so therefore, if we look at these images here, the only one that's really preserves most of the information is D. Okay, and so we would assign D going to 1. All right. Yeah, no worries. This is just to help you. So if you looked at the wrong thing, that's fine. Okay. So anyways, yeah. So D would go with 1, and now let's look at B. So B has obviously edges like this, right? So this is going to correspond to 2 because that's kept that information. So we know that this is going to go here, and then by process of elimination, C should go with 3. But let's just double check. So this should have information about edges like this, and we zoom in on that. In fact, this does have those edges. All right. So if you understand that, that's good. And if there's any questions, let me know. Just you can type into the chat or you can chime up. So is that clear to everybody?
I had a question about the center of the transform. So you said that
Sure.
the center of the Fourier transform is the mean of the values in the image.
Yep.
Um, so then does that mean the center will change, like could change drastically depending on the image if you had a really low, uh, like low brightness image that had a lot of dark spots, or like a really high brightness image that had a lot of white spots?
Yeah, I mean overall, the like if you just made the image brighter, then the Fourier transform would also get brighter. But the relative ratio of the components wouldn't change, right? It just changed that. But yeah, that's true. I mean, you can actually design images, or you can design sort of arbitrary patterns or images that would have zero at the center of k-space as long as the mean is zero, right?
Okay.
But for most biological images, there's like if anything that has mass, there's going to be protons, and so you're basically counting up all the protons at the center of k-space.
Okay. Thank you.
Okay, sure. Great question. Okay. All right. So since you guys did so well on this last one, so now this is you're going to match 1, 2, and 3 on the top to A, B, and C, and just go ahead and enter that into the chat. Let's maybe not just go ahead and enter a little more quickly so we can sort of move on. But I will wait till about half of you have entered answers just to make sure we get a sense of how people are doing. Okay, it looks like there's some consensus on this, but let's just take a closer look at this. So once again, we can sort of play the game here and say, on the top, we have these different Fourier transforms. So which one of these, 1, 2, or 3, has the least amount of information, would you say? Is it 1, 2, or 3? Just go ahead and put in your chat what you think it is. Okay, so yeah, so this clearly has the least amount of information, right? It's got the smallest part of Fourier space. And so then we can say, well, 3 corresponds to which one of these? Well, the image that looks like it has the least amount of information is clearly A, right? So we know that A should go to 3, all right? And now we want to just line up the edges. And so remember, this one here, 1 is going to have edges like that, and 2 is going to correspond to edges like that. And so we just match where the edges work. And so this one would go with here, B would go with 1, and then C would go with 2. Okay. So I think that so that did seem to be the issue where did I get this right? Yeah. So I think a lot of you had C going with 1. So do you guys understand why it doesn't go with 1? I think everyone picked C going with 1. So let's make sure we understand why. Yeah. Does everyone understand why C goes with 2? Any questions on that? Okay, so great. So I assume that means everyone understands. If not, you will there'll be some additional quizzes coming up. So we'll look at that in future quizzes in the homeworks and stuff. Okay. Okay, the last one is 1, 2, 3, and 4, going with A, B, C, and D. So go ahead and take some time and look at that, and we'll regroup once we've gotten some responses on that. Okay, looks like there's pretty good consensus on that. So let's take a look at that. So first of all, if we look at A, B, C, or D, right, in terms of the Fourier transforms, oops, which of these A, B, C, or D is only going to have horizontal components to it? Is it A, B, C, or D in terms of which one is not going to have diagonal components? Okay, right. So it's going to be B because this is solely on the kx axis, right? So if we look at these images, they all have diagonal components except for one, right? One has purely vertical artifacts. And so this must go with this. Okay. So B goes with one. And then we say, okay, of the remaining images, which one sort of looks like one? Okay. So this one here, three sort of looks like one, but just got these diagonals on it, right? Okay. So then C would go with three. And we can double check. We can draw a line out to there, and we can verify that those edges go like that. Okay, so now we just have to figure out what A and D go with. All right, and so I think let's see. Yeah, so most people got that C went with three. That's great. Okay, and then the last two are pretty easy, right? We know this has edges this way, and so this must go with two, and then by process of elimination, A goes with four. So great. Okay, so I think you guys are getting the hang of it. That's really good. So as long as you have this basic understanding of how different parts in Fourier space correspond to your image, that's really should be good enough for will be helpful for the MRI portion of the course. Okay. So if there's any more questions, just let me know. But we're going to continue. So we're going to talk a little bit about computing Fourier transforms now. And so as some of this is review, so I'll go through this fairly quickly because Professor McVeigh also talked about this in class. So remember, the delta function has a special property that it sifts out the value at where it takes on argument of zero. So obviously at x equals zero, this goes away. And so therefore, basically just sifts out the value of this at zero, which is one, okay? This sifts out the value at x naught. So this just becomes, we plug in x naught for here, and this just becomes this. And so these are sort of simple things to remember that are very useful. And then the Fourier transform of the rect function becomes a sinc function. And that's probably one of the more important things to remember, that rect goes to sinc. Okay. We can also write this rect of x goes to sinc of kx. Okay. So these are some of the most important Fourier transform pairs to know about. Now we can also ask, what's the Fourier transform of one, right? And then we end up with this weird thing, which doesn't really have any meaning to it. Okay. So it turns out you need to go back to sort of what's called generalized functions, which we're not really going to spend too much time on now. And so I'll just tell you the answer. The Fourier transform of one goes to delta function. So that's already one of the first important Fourier transform pairs we need to know. Delta x goes to one, and one goes to delta of kx. All right. So that's an important pair to know, a sort of set of pairs of functions to know about. So similarly, we can look at, and these are also very important, that if I have a complex exponential with a frequency of k naught, then the way I look at it in terms of k space, it just has energy at k naught. Okay. And similarly, cosines and sines we're going to use quite a lot. And remember, cosine is just e to the j 2 pi k naught x plus e to the minus j 2 pi k naught x over 2. And so this is going to have 1/2 at k naught and minus half at minus k naught. So that's this expression here. Okay. So complex exponentials and cosines and sines are all related. And so as long as you remember this, then it's quite easy then to figure out what it is for the sine and the cosine. All right. And this is just a depiction. We don't need to go over that. We'll just skip over that for today. Now, notice that we said that the Fourier transform of a complex exponential goes to delta kx minus a. And we also know that delta x minus a goes to e to the minus j 2 pi kxa. These look like they're almost sort of reverse of each other, except for this minus sign here, okay? This is an example of duality, which is that if I, in this case here, if I take the Fourier transform of here, I've taken delta kx minus a of delta x minus a, then it just equals g of minus kx, okay? So, for example, in this case, if I say I take the Fourier transform of delta x minus a, okay, that's just equal, so that's this function, but I just replaced x with a, kx with x, then it should be e to the j 2 pi a, let's see, yeah, of minus kx, right? And that is the answer, e to the minus j 2 pi kx a, okay? So where duality comes in really importantly is, for example, the Fourier transform of a sinc function, which if you had to evaluate this would take you some time to do, right? But you can use duality to recall that the Fourier transform of rect equals a sinc function. So therefore, we know the Fourier transform of a sinc function just equals rect of minus kx. But since rect is even, that just equals rect of kx. And so that's the next pair that's very important to remember, that the rect, we said rect of x goes to sinc of kx. And the other thing that's very important is then that sinc of x goes to rect of x. Okay, so that's another Fourier transform set of pairs that will come up all the time, especially when we're doing MR. The other important thing to realize is what happens if a function is separable, which means that I can write it as a product of a function of g of x and a function of gy of y. If it's separable, then the Fourier transform is just simply the product of the individual 1D Fourier transforms. So the classic example is shown here, where I have rect of x times rect of y, and this equals sinc x, sinc ky. Now, warning, a lot of times students say, well, if I have rect of x times rect of x, that equals sinc of kx times sinc of kx. This is wrong, okay? Because these are both x's, okay? So there's no separability there. And in fact, we're gonna have to use a different theorem for that. So this only works if you have a function of x and a function of y, not two functions of the same variable, okay? So just keep that in mind that this is very wrong, okay? Here's those pictures. So this is a function we will use all the time. And we use it so often that we'll also just give it the name rect of x comma y. All right. And this, as we said, that goes to sinc of kx times sinc of ky. And we'll use this so often that sometimes we'll call this sinc kx, ky. Okay. It's just sort of abusive notation, but you might see that sometimes. Okay. So I'm going to launch a poll, and let's see, let's launch this poll. Okay, so there's a poll out here. So the question is this function separable? So if it's yes, pick A, and if it's no, pick B. All right. Just take a look at that function and enter A for yes if it's separable, and B for no if it's not separable. Okay, look, so those of you who responded, about 80% said yes, and 20% said no. So let's look at that. So indeed, we could write this as e to the minus j 2 pi 8x times sine 28 pi x, right? Times e to the minus j 2 pi ny, right? So this is a function of x and this is a function of y. So yes, it is separable. Okay. So now let's take a look at how we would calculate the Fourier transform of this. So we can sort of see this has a value. This corresponds to sort of a value of k naught equals -9. So this would go to Fourier transform ky plus 9. Okay. And now here we have to be a little careful, right? Because remember, these are two functions of x, so we can't just take those separately. So we'd have to really write it down. We have to write this is e to the minus j 2 pi 8x times e to the j 2 pi 28x minus e to the j 2 pi 28x all over 2j. Okay, so that equals 1 over 2j e to the j 2 pi 20x minus e to the, oh, sorry, this is minus j 2 pi, minus j 2 pi, I guess that'd be 36x, right? And this would go to a delta of kx minus 20 minus delta kx plus 36, all multiplied by 2j. All right, so that's just applying the what we just did. So that's an example of how you can sort of take a function that looks sort of complicated and just boil it down to these very simple delta functions, because we know complex exponentials go to delta functions, right? So that's a good thing to work through on your own. And here's just to make sure you understand that. Here's some other examples that are fairly easy. So delta xy equals delta x times delta y. Both of these go to 1. So 1 times 1 is just equal to 1. Okay. This one on the bottom, sort of a trick question. This is actually equal to delta x times 1, right? So this goes to delta, this goes to 1, and this goes to delta ky. And so when we multiply them together, I get delta ky, right? Just because I told you this is a function of x and y, and so the implicit function as a function of y is just 1, all right? Okay, so this is just summarizing a lot of what we talked about. So we talked about most of these pairs, and so this is a useful sort of slide to have at your reference. The book also has one here. The only thing to keep in mind is, remember, this is kx and this is ky. Okay. Okay, so now we're going to talk about some of the most important properties that you should keep in mind. So I think we have about 25 minutes, so that should be enough time to get through this. Once again, this is really meant to sort of as review, but if there's questions, let me know. One of the most important properties is that the Fourier transform is linear. So if I take some function of g and h, and I multiply both by scalars and I add them up, then the output is just that scalar times the Fourier transform of g plus the scalar times the Fourier transform of h. Okay, so linearity is Fourier transform is linear, which makes sense because the Fourier transform just involves multiplications and addition. in terms of the multiply, and the integral is just a form of addition. So it should be linear. We'll just walk through one of these examples here. So this is a simple example here where I have 1 plus e to the minus j 2 pi ax. And remember, 1 just goes to the delta function. And then since it's linear, I can just add on the Fourier transform of this. And remember, this is equal to e to the minus j 2 pi x times 1. So that's going to give me a delta function kx plus a and a delta function of ky. All right. Okay. Probably one of the most important properties is the scaling theorem. And what that means is if I take g of a of x, then the Fourier transform is a scaled version of the Fourier transform of g. And if this is ax, this is going to be kx over a. Okay. So let's look at an example of that. Here's rect of x. Okay. And here's rect over 3x. Okay. And since 3 is greater than 1, that means that I'm actually squeezing that function. Okay. So rect of 3x is going to be narrower than rect of x. And then here we know rect of x goes to sinc of kx. And now applying the theorem, in this case, a is equal to 3. So I get 1 over the absolute value of 3 times sinc of kx over 3. And that's shown here. And so you can sort of notice here that sinc of kx over 3, since we're dividing by 3, that's going to be much broader than sinc of kx. And also I'm dividing the overall amplitude by 3, so the amplitude is also lower. Okay. And so essentially, the most important thing to remember is as you squeeze a waveform in one domain, it expands in another domain. And similarly, if you stretch it in one domain, it will squeeze it in the other domain. So Professor McVeigh has talked about modulation transfer functions. And essentially, that is just the Fourier transform of the point spread function or the line spread function. We can call this point spread function here. Okay. So this is sort of like, your h of x is here, right? These are your impulse responses. And then these are their Fourier transforms, the modulation transfer function. So you can sort of see here, going from here to here, I broaden my impulse response. And so therefore, if I'm expanding it in one domain, and then the Fourier transform is getting narrower. And the more I expand that impulse response, the narrower my Fourier transform gets, which makes sense. Basically, the fatter my impulse response is, the more it's going to blur things out. So I'm going to lose these high frequency components. Okay. So that's how you think about something like that. Okay. And so in class, for example, the way we look at these things is these are different phantoms with different frequencies, and how well your system can resolve this tells you something about the frequency response. And so, for example, if your system is really falling off and can't detect high frequencies, then this will all be blurred out, right? So the modulation transfer function you can think of is you can put in sinusoids of different frequencies, and these are all of amplitude 1. And then the output basically is shown by the dotted line here. You can't really see it here. And so that's smaller. So basically showing the response is going from, I put in 1, I get out 96 at this frequency, 85, 68. And here, the output is 7, right, at this high frequency of 3. And so that's telling me my frequency response would be going down like this, like from 96 down to 7 as a function of frequency. Okay, so that's sort of the Fourier transform of my system is the frequency response or the modulation transfer function. And those are both basically, the MTF is essentially the Fourier transform of my impulse response. Right, so that's just shown there, so I didn't have to draw it. Okay, so let's look at this one here. Okay, I mean, it's a simple question, but just to check, let me relaunch the poll. Let's see. How do I end this? And relaunch. Okay, so there's A, B, and C. So which of those, so it's referring to figure one here. So which of these has the best spatial resolution? A, B, or C? Okay, so it looks like most of you are picking C, so about 80% are picking C. So that is correct. C is the narrowest, right? So that has the best spatial resolution. There was a choice of A, but see, A is the broadest, right? So it would sort of have the most blurring, and so that would have the worst spatial resolution. So the answer is C. So that's good. Okay. Let's do another poll. Let's see. Let's relaunch the poll. Okay. So now it's saying that so we want to, so C, right? Let's say C is what we want to say, which of the MTFs corresponds to, so which of these here is the one that corresponds to C? So pick A for MTF1, B for MTF2, and C for MTF3. Great. So it looks like there's unanimous consensus. Everyone picked C, which is the broadest response, and that makes sense because it's corresponding to the narrowest H impulse response. So the frequency response is going to be the broadest. Good. So that's really good to keep in mind as you're sort of moving forward with imaging. Okay. So another really, really important thing that we're going to use all the time is what's the Fourier transform of a convolution? And so this is now where I have g of x convolved with h of x. And it turns out the answer is just I multiply the two Fourier transforms by each other. Okay. And remember, this is not separability. Right? Because remember, in separability, that was Fourier transform of g of x times h of y. Okay. But now here, see, both things are both kx or x. Okay. So that's why now it's convolution that goes to multiplication. And the dual is if I multiply this, okay, then I have to convolve in the other domain. So this is actually not separability, okay? Previously, if this was x and y, I would just multiply here kx and ky, the Fourier transforms. But here, Fourier transform of the product of g of x, h of x is equal to g of kx convolved with h of kx. So that's really important to remember. So let me just talk you through why this makes sense. Remember, we can take any function like this and convolve and decompose it into different Fourier components, right? Different sines and cosines. And we notice that, for example, the Fourier transform of this is just the amplitude of each of those frequencies, right? So we can have some Fourier transform like this. And then we pass g of t through some system which has an impulse response h of t, okay? And that's going to have some Fourier transform like this, which is going to modify these input frequencies, okay? And so you can sort of see that if I have this, it's going to be multiplied by this. If I have this, it'll be multiplied by this. This will be multiplied by that. So this is going to modulate each of those input frequencies, okay? So now I assume G of t, y of t is the output of G of t convolved with H of t. And so that's just going to, because of this picture here, that's just going to lead to different each of these input frequencies is modulated by by this modulation transfer function. And so therefore the output frequency should just be my input multiplied by my modulation transfer function. So here I have multiplication, and that's going to be the Fourier transform if I took G of t and convolve with H of t. And so that's the convolution in the time domain here is resulting in multiplication in the Fourier domain. Okay. This is just going through the math. We don't need to go through that too much. But just to remind you, here I'm writing G of x. Sorry. Whoops. H of x is written as its inverse Fourier transform. And so Z of x is just taking that Fourier transform and multiplying it by the impulse for the modulation transfer function, which is the Fourier transform of this, and then taking its inverse transform. Okay, so this is what we're seeing here. And this just turns out to be because complex exponentials turns out to be eigenfunctions of the convolution operator. So that just means that anytime you put in a complex exponential into a linear time invariant system, the output is just going to be a complex exponential of the same frequency, but different amplitude and different phase, right? Okay, so let's look at the most important, one of the sort of a simple application of this, which is, let's say I gave you this function, the triangle function, which is, whoops, it looks like this, okay? And if you'd had to take the Fourier transform of it, then you'd have to take the Fourier transform of this. And you could all do this, with having taken out calculus, but it might take you a little bit of time, okay? So what's a simpler way of doing that? Well, you could just say that I know that the rect function from last week, last supplementary section, is just a rect times convolve with a rect. The triangle function is rect convolve with a rect. Therefore, convolution theorem, I take a sinc and I take a sinc here, and those get multiplied together, and so I get sinc squared. So the Fourier transform of a triangle function is just sinc squared. And so you can write down the solution without having to do any calculus or any algebra. So what we just described also holds in 2D. So if I do a 2D convolution, which you did in homework 1 MATLAB, then that just leads to a multiplication. And also I do multiplication, that leads to convolution. So we'll see this again in MRI, but let me just show you an example of that here, which is here, assume I have this object here, which is a rect function, and it has this Fourier transform, which is a 2D sinc function, okay? Now I ask the question, what happens if I multiply the Fourier transform by this rect function? Well, this rect function just zeroes out it only keeps stuff in the center, and so this is the resulting multiplication of those two functions, right? I took this function and multiplied by this function, and I get this function. So that's multiplication in the frequency domain. So that means I have to, in the image domain, I have to take my original object. I take the Fourier transform of this rect function. The inverse Fourier transform is just a sinc, right? Because rect goes to sinc. And now I have to convolve this with this, okay? So that means everywhere I have sort of a dot here, I replace it with this sinc function. And so that convolution, just like when you convolve the cross with the Gaussian, that's going to tend to blur out your object, okay? And so that's multiplication in one domain leads to convolution in the other domain. So what that means is if I have an imaging system where I have like module 1, module 2, module 3, and I can represent the output as, let's say my input is G of x. First I convolve with H1, then I take that output, convolve with H2, and then I take that output and convolve with H3. That would give me my output. So essentially each of these is like a module you would go by. Maybe one is an amplifier, and another is a filter, and you put these modules together in the lab, okay? And then it turns out that the overall frequency response is just the output is just the impulse response, the frequency response of the input multiplied by the modulation transfer function of the first module a second module, and a third module. And so convolution in this domain gives me multiplication in this domain. Okay, so let's look at this system here and imagine that this was a system where we had module A, module B, module C. Okay. And I'm going to ask you all to think about this for a little bit and say, okay, so if I gave you $1,000, okay, which module should you replace and get a better module? Should it be A, B, or C if you want to make the system response better? Okay, good. So it looks like 80% of you picked A, which is the correct answer. So remember, the system response here is just sort of the H of A times H of B times H of C, right? The frequency response is multiplied together. So in this case, it's clear that A is really dominating our narrow response. And so we can make A a little bigger, then that will improve the system response. And so in this case, if your advisor said, hey, the system response is too narrow, the frequency response is too narrow, it's cutting out all these high frequencies, we need to get those high frequencies back, then you would want to go back and sort of pick A and get A to be broader, and then the overall frequency response would then be broader. So that is correct. So it looks like 71% of you picked A, so that's good. Okay, the final thing a couple of things we're gonna talk about will also be used in the class, which is the modulation example. So here we can take, what happens when we take some function g of x and multiply it by complex exponential? Well, here that's multiplication in one domain, so that means we convolve in the other domain. And so that means we take g of kx and convolve it with delta kx minus k naught. And remember from the last supplementary session, anytime I take a function and convolve it with a shifted delta function, it just shifts the function, okay? So that's a very important property where multiplication by a complex exponential in one domain shifts the Fourier transform. If I do a cosine, remember the cosine has a delta function at k naught and minus k naught. So it's going to input two shifts, one shifting to k naught and one shifting to minus k naught. So the most sort of prevalent example of that, I'm not sure anyone has listened to AM radio, but AM radio was one of the first ways that people figure out how to broadcast radio waves. And so what would happen is we would take an AM radio, you take like a sound. So G of T could be like your voice, right? And then it turns out that the wavelength of your voice, the electromagnetic wavelength of your voice is just too long to really transmit efficiently. So you need to modulate it up to some carrier frequency, in the order of say 100 kilohertz or so. So an AM radio frequency. So then basically you take that waveform and you multiply it by a cosine of a higher waveform. And so now you get G of T times cosine 2 pi F naught of T. So I've done a multiplication in the time domain. So if we think about in the frequency domain, let's say this is the Fourier transform of your voice waveform. Since we multiply in one domain, we know we're going to be shifting, we're convolving another domain, and we're going to be convolving with shifted delta functions. And so that just shifts this and creates these replicas at higher frequencies. So now these are centered at F naught and minus F naught. And so since F naught is at a frequency that you can broadcast easily, you've taken your original waveform, moved it up to a frequency that's better for broadcasting, and that's why it works for radio, okay? So modulation is used all the time. So for example, your phones are taking your voice waveforms and modulating those. And it's much more complicated than this, but it's the same idea. You're multiplying a waveform by some other waveform. Okay, so here's a modulation example. Let's say we take my rect function here. Oops. And I multiply by this stripy pattern here, right? And so this leads just to a stripy pattern that's confined to the rect. So this is multiplication in this domain. That means in this domain, I've got to convolve. And so here I have the rect function goes to 2D sync function. I'm going to involve it with this, which I think is just too hard to see. There should be two little dots here like that. Okay, so two little delta functions, because this is a cosine that's going to end up with two delta functions along the kx axis. And so this is, when I convolve this with this, that's just going to take that and shift it here and then shift it there. Okay, so this would be the resulting Fourier transform of this function here. Okay, so I modulate in one domain, it leads to a shift of the waveform in the other domain. So another example of that is the shift theorem. And so we also know that if I shift in one domain, like I take an object and shift in one domain, that's just going to lead to multiplying it by a complex exponential in the other domain. So that's the example of duality, okay? I think we can skip this example for today. Let's talk a little bit about conjugate symmetry. This will be the last thing we'll talk about. It turns out that the Fourier transform has this interesting conjugate symmetry, which is if I know the values of g of kx, then I also know something about the values at the minus kx, okay? And similarly in 2D, if I know the values at kx and ky, I also know what the values are at minus kx and minus ky, okay? They just turned out to be the complex conjugate of each other. So it turns out this is really useful and used all the time, for example, in MRI, because it means if I know the Fourier transform here, then I also know the Fourier transform there, okay? So it means that I don't have to collect all the data in the Fourier domain. And so typically what's done is, for example, in what's called partial Fourier, which you can read about more here, I just acquire part of the data in the Fourier domain. And then I use this property to figure out what the data is in the part that I didn't collect. And what we find in MR is this takes time to collect data. Okay, I've got to go through K-space. We'll talk about this when we do MR. And so if I don't have to collect this data, I can save myself a lot of time. In theory, I could go twice as fast. In practice, the gain is more on the order of I can collect, 75% of the data. And so I could go maybe 50% faster, but not 100% faster, okay? Okay, so just to summarize, this is the basic properties. We talked about linearity, scaling, separability, duality, shift, convolution, multiplication, modulation. The book also has similar organization of the properties, including some we didn't talk about, just with different notation. Once again, U and V are Kx and Ky. Okay, so that's all I had for today. Hopefully this was useful to some of you. And are there any questions before we end today's session? Okay, if there's no questions, I'm going to stop the